In this third episode of trigonometry, we shall be looking at addition formulae. And once again, I'm Bright Wokwesiga Nelson Amoti, a teacher of advanced level principal mathematics. We shall be looking at addition formulae, and we have already had the previous episodes where we introduced trigonometry. We looked at ratios of common angles and the quadrant system. And now we are looking at the addition formulae. The addition formulae is used to express trigonometric ratios of the sum or difference of two angles in terms of the trigonometric ratios of those similar angles. For example, if we have the sine of A plus B, can we express that in terms of the ratios of the individual angles A and B, like sine A, cos B, and all that? We shall make use of the following trigonometric identities. These ones can be derived, but I didn't want to delve into that. Our key learning outcomes is to know these identities and be able to apply them in proving trigonometric identities. We have 6 major identities in the addition formulae, and 4 of them can be memorized directly. The last 2 can be derived from the first 4, as we shall be seeing. If you don't have our guiding notes on this, I expect you to pause the video and be able to copy down these 6, as we shall be applying them along the way. So the first 4 as they are, note that in the first 4 for sine, for addition, even after expanding, it remains an addition. But for cosine, addition here it turns into subtraction. There is a major shift. Students always confuse that one. Then even for sine A minus B is sine A cos B minus cos A sine B. But for cos A minus B, there is a plus in the middle after expansion. So it is we have to go down very carefully, because it will be affecting us, and it is a very common mistake. However, if you don't recall these ones offhand, which is very important to recall, but in case you fail to recall, or you forget something, or you doubt an expansion that you are about to make, you can still visit the mathematical tables and list of formulae book that is always given to us during examinations. Allow me use the first 4 identities to prove the ones for tan. So we shall use these 4 to be able to prove these 2. Let me begin with the tan of A plus B. Now, tan A plus B is the same as we saw before. Tan is a ratio of sine cos, sine A plus B over sine A over cos, sorry. So tan is sine out of cos. Now, we expand the numerator using this identity. We shall have sine A cos B plus sine B cos A. Then the denominator is cos A plus B, so we shall use this identity. No, the one of cos A plus B, we shall use this one. So it will be cos A cos B minus sin A sin B. In our proof, since we have a 1 here, it can, we are dealing with, since we have a 1 here, we can use that as a guidance. Since we are having a cos A minus cos B in the place where we have a 1, we can divide through by cos A cos B throughout. How to calculate a 1 at this point? Sin A cos B, we are dividing it by cos A cos B plus, do the same thing here, sin B cos A divided by cos A cos B. Then down we have cos A cos B divided by cos A cos B minus sin A sin B divided by cos A cos B. Now cos B goes with that. Sin A over cos A is tan A plus cos A goes with cos A. Sin B over cos B, we get tan B. This goes with that. This goes with this. Remain with the 1. That was our major item at the beginning by dividing through by cos A cos B. Then sin A over cos A is tan A. Then cos B over sin B is tan B. This one is the same as our right hand side, and therefore we have been able to prove it as required. Now you can follow through the same steps and prove the one for tan A minus tan B. You can first pause the video and you try to do tan A minus B. We now go to examples. Our question number 1 says, if sin A is 4 over 5 and cos B is 5 out of 13, and that both A and B are acute angles, this word is and, are acute angles, which means they lie between 0 and 90 degrees, which is the first quadrant. As we saw before, in the first quadrant, all the trigonometric ratios are positive. Evaluate without using tables or calculators, but we are seeing on the screen here. Now, when we expand this sin A plus B, cos A minus B, and tan B minus A, using what we have just previously seen up here, first take you back, using what we have seen here, what we have written down on your paper, you will discover that it will result in 2 singular trigonometric ratios of angles. You have these ones, you have those, everywhere that we shall be expanding and getting the tan, the cos, the sine of both angles A and B. What does this mean? It means that even before we begin the expansion, we must first look for cos A because we shall need it. We shall look for sin B because we shall need it. We shall look for tan A and tan B. Now, the simplest way of doing this is actually using Pythagoras theorem. We shall actually draw the acute angle required, and we shall have the angle A. Sin A is opposite out of hypotenuse, and we can therefore find the value of the adjacent side. Let me call it A. Now, Use Pythagoras theorem, squaring a squared plus 4 squared is equal to 5 squared. You'll be able to get the value of a. Use it as your side work. You'll be able to get the value of a as 3. What about if we get the one for b? The one for b is cos b, and cos b is 5 out of 13. So it is adjacent out of hypotenuse. So we shall need to find the opposite side. We call it small p. Still using the same approach, p squared plus 5 squared is equal to 13 squared. Shall be able to get the value of p as 12. We have just skipped those procedures, save the length of the video. You can have a pause our video and you work out that Pythagoras theorem. It should be part of your working as you are doing this kind of solution. Now, since we have got that, we can now proceed with our solution. Part A, sin A plus B. Sin A plus B, when you expand it using our first expression in the list of blue we are using, it will be sin A cos B plus sin B cos A. But we have got sin A. Sin A is 4 out of 5. Cos B is 5 out of 13. Now sin B, we shall get from here. Sin B is the opposite of hypotenuse, 12 out of 13. Then cos A is adjacent over hypotenuse, 3 out of 5. This will be 20 out of 65 plus 36 out of 65. This will give us 56 out of 65. Then part B, we have the cos of A minus B. This one is in our list would be cos, in our formula will be cos A cos B plus. Please always take note of the change of sign from negative to plus. Sin A, sin B. Now I leave it to us to substitute the values. Cos A is adjacent over hypotenuse. Cos B is 5 out of 13. Sin A is 4 out of 5, opposite over hypotenuse, and sin B is 12 out of 13. It means we shall have 15 out of 65 plus 48 out of 65. This one will give us 63 out of 65 as our answer. We now proceed to turn B minus A. Part C is tan of B minus A. Using our last identity, which I had asked you to prove, hope you did it. It will be tan of B minus tan of A out of 1 plus tan B tan A. Then we go back to look for the value of tan B from our diagrams. Tan B is opposite. This is opposite over adjacent, 12 out of 5. Then tan A is 4 out of 3. Tan B, 12 out of 5. Tan A, 4 out of 3. Tan B is 12 out of 5. Then tan A is 4 out of 3. Out of 1 plus 12 out of 5 times 4 out of 3. LCM here is 15. So we have, of course, multiplied. 13 times 3 is 36 minus 20 out of 1 plus 48 out of 10. By simplification, we have 13 minus 20 out of 15 plus 48. Try to simplify that one. 36 minus 20 is 16. And 15 plus 48 is 63. So by doing so, we would have found the value of tan of B minus A. We now go to example number 2. Example number 2, they have given us that if tan of x plus y is 4 out of 3 and tan x is a half, evaluate tan y. So we're going to expand the first expression. Tan x plus y is equal to 4 out of 3. Now, this one, in terms of addition formulae, it will be tan x plus tan y out of 1 minus tan x tan y is equal to 4 out of 3. By cross multiplication, we shall have tan x plus tan y is equal to 4 over 3 into 1 minus tan x tan y. Now we put the value of tan x as a half. We have a half plus tan y. Now multiplying through by 4 over 3 into the bracket, you'll have 4 over 3 minus 4 over 3 times tan x. Tan x is a half times tan y. So a half plus tan y will be equal to 4 out of 3 minus by 2, 1 by 2, 2 minus 1 of minus 2 over 3 tan y. So I need to calculate terms. This can go to the left while this comes to the right. I will have tan y plus 2 out of 3 tan y to give us 4 over 3 minus a half. tan y plus 2 over 3, we shall get 5 out of 3 tan y. This cell shall have an LCM of 6. This is 8 minus 3. So we shall have 5 out of 3 tan y is equal to 5 out of 6. By 5, 1, by 5, 1, by 3, 1, by 3, 2. Which means tan y is equal to a half. We have got the value of tan y. We now proceed to question number 3. Show that cos 180 degrees minus a is equal to cos a. Shall begin with the left hand side. We have cos 180 degrees minus a, which is the same as cos 180 degrees cos a plus sine of 180 degrees sine a. The cos of 180 degrees is negative 1. How have I got this one? 180 degrees is the same as 180 degrees minus 0. Now cos of 0 is 1. Cos of 0 is 1. And because if I do this, cos of 180 degrees minus 0 degrees, I'm trying to make it be as if it's in the second quadrant. So this as being my acute angle 0. This is the same in the second quadrant. Cos is a negative. So we have cos of 0 degrees, but negative because in the second quadrant cos is negative. Now cos of 0 is 1. Get negative 1. We saw this one when we're dealing with the quadrant system in our second video. Now negative 1 times cos a plus sine 180 degrees is 0. Then sine a, which is negative cos a plus 0, which is negative cos a. This gives us our left hand side as required. Question number 4 says, show that cot x plus y is that. Still using our left hand side, shall expand cot x plus y is the same as cos. For cot is cos over sine out of sine x plus y. Then we expand up. For cos, we use cos x cos y minus the side changes, then sine x sine y. Out of, down we have sine x cos y plus, for sine the positive side is maintained, then sine y cos x. You just interchange the ratios for the different angles. Then since we need a 1 here, so this thing must become a 1. So we shall divide through by sine x sine y to make that 1 there. Cos x cos y over sine x sine y minus sine x sine y over sine x sine y out of sine x cos y 0 over sine x sine y plus sine y cos x over sine x sine y. So Cos x over cosine x is cot x. Cos y over sin y is cot y minus 1, which we created, over sin x over cos x sin x goes, cos y over sin y is cot y plus sin y goes with sin y. Cos x over sin x is cot x, which is the same as our right hand side as required in the proof. Question number 5. Please forgive my speed. I'm trying to shorten the video, but you can as well pause, go back and replay so that you can understand the steps at a slower pace. Now here we have the left hand side, and we're supposed to it is equal to our right hand side. Now on the left, I'll expand these things on the left. The first one, I will borrow from this that a plus b squared is equal to a squared plus 2ab plus b squared. So I shall square the first term. Now my a is cos theta, so you will have on the left hand side, you will have cos squared theta. That now my b is this, so it will be 2ab, which will be 2 cos theta sin theta, then b squared, which is 5, sorry. Then is 2 cos cos. Is 2 cos theta cos phi, then plus cos squared phi. Now squaring this. Now plus the same thing applies here. That is my a, that is my b. It will be sine squared theta plus 2 sin theta sin phi plus sine squared phi. Some things are similar. This one and that one, we shall have cos squared theta plus sin squared theta. Then this and this are also similar. This is cos theta cos phi plus, I have pulled out the 2 sin theta sin phi. Then these two are still also similar. You'll have plus cos squared phi plus sin squared phi. From our first identities of Pythagoras theorem, we discovered that this one is 1 plus 2. Now when you look at this, excuse me, when you look at this one in the bracket here, it is the same as saying cos theta minus phi from our addition formulae. This is cos theta minus phi, then plus a 1 the other side. Now 1 plus 1 is 2. 2 plus 2 cos theta minus phi. We would have got our right hand side. as required. It was about factorize 2, but it is found that in our proof the 2 has been left there the way it is. So that is the end of our proof. Now we go to question number 6. Question number 6 had a typing error initially, so when I was doing solving it, I skipped it. But in your, as you can see in your notes that I have shared, number 7, show that tan pi over 4. Don't forget that pi over 4 in radians is the same as 45 degrees. Pi over 4 plus x tan pi over 4 minus x is equal to 1. Still begin on the left, tan pi out of 4 plus x tan pi out of 4 minus x. This one becomes tan pi over 4 plus tan x over 1 minus tan pi over 4 tan x. I'm trying to use our identities for addition formulae for tan. Then for this one it will be tan pi out of 4 minus tan x out of 1 plus tan x tan pi out of 4. Now when you recall from our ratios of common angles, we shall discover that tan 45, this one, tan pi over 4 is 1. So whatever it is, we can now put a 1. 1 minus 1 times tan x, which is tan x, times, this is 1 minus tan x out of 1 plus tan x. Because our tan 45 or tan pi over 4 is a 1. Now some things here will divide. This will divide with that. This will divide with that. And we end up with a 1, which is our right hand side. Hence has been proven as required. Next question we have, if tan lambda is equal to mu, if tan lambda is equal to mu, show that sin theta plus mu cos theta over cos theta minus mu sin theta is equal to tan theta plus lambda. Now we have already been given the value of mu, which we can proceed to substitute in our expression. Sin theta on the left hand side, sin theta plus mu, but mu is tan lambda, cos theta out of cos theta minus mu, but mu is tan lambda, sin theta. Now I can now change tan lambda into sin lambda out of cos lambda, then cos theta out of cos theta minus sin lambda out of cos lambda, then times sin theta. I can now proceed to multiply through by, I can multiply through by cos lambda. This is one of the, here I'm going to show you two paths from here. which you can proceed by. The first one is multiplying through by cos lambda, and you get cos lambda sin theta plus, here cos lambda goes, you remain with sin lambda cos theta out of, down you'll get cos theta times cos lambda, you get cos theta cos lambda, and minus, here cos lambda goes, multiplying it there, you remain with sin lambda sin theta. Here we are multiplied through by cos lambda. Now the one up, if you look at it very closely, it is like saying sin A cos A plus sin B cos A. So the one up is the same as the sine of theta plus lambda. And the one below, looking at it closely, will be cos, in terms of addition formulae, is cos theta plus lambda. The negative becomes a plus. It gives us sine over cos of the same angle is tan theta plus lambda, which is our right hand side as required. That is if you deal with it in this angle. Again, from here, you can deal with it differently. Since you want tan, at this moment I can divide through by cos theta throughout. Then we have sin theta over, and I'm giving you a different approach from this stage going downwards. I'm dividing every term by cos theta plus sin lambda over cos lambda out of cos theta over cos theta. I'm dividing every term by cos theta, then sin lambda over cos lambda times sin theta out of cos theta. Sin over cos is tan. Sin over cos is tan lambda. Cos over cos is 1. Sin over cos is tan lambda. Sin over cos is tan theta. You look at this thing. It is an addition formula for tan of theta plus lambda, which has proved our right hand side. So there are very many interesting ways of solving these questions. It depends on your level of creativity and practice. We got the next question. I have somehow rearranged. I'm beginning with number 10, then we shall come to number 9 later. If sin x minus alpha is cos x minus alpha, show that tan alpha is tan x minus 1 over tan x plus 1, also the same as tan x minus pi over 4. This proof here is transitional. It goes through 2 stages. Now let's begin from the basic one. In most of these if statements, we begin with the first condition and it gives rise to the required proof. So we have sin x minus alpha is equal to cos x minus alpha. This becomes sin x minus alpha over cos x minus alpha is equal to 1. Now sin over cos is tan. X minus alpha is equal to 1. Note that here I've taken one approach. Another one can first move from this step and expand in terms of the formulae for sin and cos, then proceeds differently. Now I have got this, I can now expand. I will have tan x minus tan lambda out of 1 plus tan x tan alpha, sorry, is equal to 1. Now here I want to make tan alpha subject. I will have tan x minus tan lambda is equal to 1 plus tan x tan alpha. I've just cross multiplied. Now I want to find tan x. So I will simplify it by collecting like terms. Terms which have tan x. I will have tan x into 1 minus tan alpha, sorry. I think our aim is to get tan lambda, not tan x. So this step I'm doing is going to lead us astray. So I'm going to first bring in tan lambda together, tan alpha, sorry. Let this tan alpha go that side, and the 1 comes this side. So you'll have tan x minus 1 is equal to tan alpha plus tan x tan alpha. So tan x minus 1, tan alpha is common, 1 plus tan x. Divide through by 1 plus tan x. Divide through by 1 plus tan x. This goes with that. You have tan alpha is tan x minus 1 out of 1 plus tan x. Now, how do we move from here? The middle we have shown. Now we have to move from the middle part to reach the right-hand side. Now, since they have introduced here the pi over 4, which is 45 degrees, we also have to think about introducing it. But recall that tan 45 is 1. So we can create this one to resemble the addition formula for this. And make it tan x here. Here it would have been minus tan 45, which is okay because it is 1. So tan pi out of 4. That is still a 1, so I haven't made any change. Then 1 here is okay. In our formula, it's supposed to be 1 plus tan A tan B. Now, this is tan x, which I can take it to be times 1. It's still tan x, but that 1 is tan 45. So this becomes tan of x minus 45 degrees, or pi out of 4 radians. And hence it has been proved as required. Can now do our last question. I had reserved because it was more complex than number 10. I wanted to move from simple to complex, not otherwise. Now here we have tan A plus B plus C. This is my left hand side. Now, What if we break down this angle so that it becomes A plus B, then plus C? When you're moving with me, so you can instead say, you can first group B and C. Then you see if you end up with the same thing. Let's say tan A plus bracket B plus C. Then you open alongside what I'm doing here. Now using the addition formula, this is tan A plus B plus tan C out of 1 minus tan A plus B times tan C. Again, tan A plus B is tan A plus tan B out of 1 minus tan A tan B plus tan C. Again, here we have tan A plus tan for this one plus tan B out of 1 minus tan A tan B then times tan C. When now multiplying through by this by 1 minus tan A tan B throughout, we shall have tan A plus tan B. If I multiply through by this numerator, it goes away, cancels, but here it remains tan C into 1 minus tan A tan B out of 1 times this gives us 1 minus tan A tan B, but here it cancels out times this, here it goes, we remain with the minus tan C into, that one remains the way it is, into tan A plus tan B. So what do we get? We get tan A plus tan B. Now here we multiply tan C times A is tan C. Then tan C times tan A tan B, we get minus tan A tan B tan C. That's a product. Out of, now we are here, 1 minus the denominator, 1 minus tan A tan B minus tan C times tan A, we get tan A tan C. Then tan C times tan B, we get minus tan B tan C. I think this one is the same as what we had on our right hand side. True. Just a slight rearrangement, but it's still the same thing. Now this marks the end of our third episode on trigonometry, which has been addition formulae. Keep following our channel and also get involved in our math clinic discussion group. You can be added by contacting the number in the video description, and that number is 0781 22 633 93, so that you can move with us in every step we are taking.